In this video, we'll discuss the limit laws and the limit of a composite function. These are actually very simple, so this video will be very brief, but I just wanted to cover them because the material is covered in the calculus text. So the first one is that the limit as x approaches c of some constant k is equal to k, and I think that it's obvious when we look at an example. So if I have limit as x approaches 2 of 3, what I'm doing is I'm looking at the graph of y equals 3 in the vicinity of x equals 2. And you're saying, okay, well, what are the y values approaching? As x approaches 2 from the left, the y values approach 3. As x approaches 2 from the right, the y values approach 3. So of course the answer is 3. This law just says that the limit as x approaches a constant of a constant function is the value of the constant function, because graphically, obviously that's true. The y values are 3 as you approach from the left, and they're 3 as you approach from the right, and they actually are 3 at x equals 2 in that particular example. This one is also very similar. It says the limit as x approaches c of x is equal to c. So you're asking yourself, well, what happens to x as x approaches c? Well, x approaches c. I mean, the function is so simple that it seems really silly to even look at it. But just to make sure we understand it graphically, this is called the identity function. It's just y equals x. Nothing fancy. And let's say we're looking at, let's say x equals 3 again. I think we can see just, of course, the answer is going to be 3. Because as x approaches 3, of course, x equals 3, or x approaches 3. But if you want to look at it graphically, this is what you're thinking about. You're thinking, I've got a function y equals x, and I'm interested in what happens to the values of that function as x approaches 3 from the left and the right. Well, since it's a linear function, and since it's a very simple linear function, the identity function y equals x, it just approaches exactly what you would expect. It approaches a 3. And then we've got something very similar. The limit as x approaches c of x to the n is c to the n. So let's take the limit as x approaches 2 of x, I don't know, squared. Let's draw a graph. Y equals x squared is a parabola, or it has a graph that is a parabola. So in general, it's going to look like this. And the question is, well, what happens to the y values as x approaches 2? As x approaches 2 from the left, the y values approach 2 squared. As x approaches 2 from the right, the y values approach 2 squared. So we just get 2 squared, which is 4. You just plug in the 2, you get the 4. But that's the limit of one of our continuous functions. X to the n is always continuous. And for x squared, it happens to look like this. But all you do is plug in the x value. Now, here are the limit laws, like standard limit laws. We're going to say that f and g are real valued functions. That means you're going to put in a real number and the output is a real number. And we want the limit as x approaches c of f of x to be equal to L, and limit as x approaches c of g of x equal k. L and k are finite numbers, so these are well-defined functions. And here are our limit laws. This just says the limit as x approaches c of b times f of x is just b times L. Or in other words, like you can factor that constant out and then just multiply that constant by the limit of the function f of x. So if you wanted to, I guess we could draw it or write an intermediate step. The limit as x approaches c of b times f of x is b times the limit as x approaches c of f of x. And this quantity right here is L. It's pretty simple. We've got the limit as x approaches 1 of 3x. That's just 3 times the limit as x approaches 1 of x. And of course, this is equal to 1. You just get 3 times 1, which is 3. So of course it's true. if I take this function and I multiply it by 3, so everything is 3 times taller, shouldn't the value of the limit just be 3 times the original limit? Well, yeah. And that's what that limit law says. And this says, take the limit as x approaches c of f plus or minus g. And that's actually 2 limit laws. F plus g is one value, and then f minus g is the other value. So you're just looking at the 2 y values on those graphs. The y values on this graph and the y values on this graph. And you say, well, these y values are approaching L, and these y values are approaching K. What happens if I add them together? What happens if I subtract them? Well, you just subtract the limiting values, or you add limiting values as appropriate. So they're pretty much telling you exactly what you would expect, that you just take the limit term by term. If you have an expression involving multiple terms, provided all of those limits are finite, all you have to do is add or subtract them. And if there are constants, you can pull the constants out and then multiply those constants by the limit of the corresponding function. So super easy example, limit as x approaches 2 of, let's say, 2x squared plus 5x minus 1. It's going to be 2 times 2 squared plus 5 times 2 minus 1. So I'm taking out that 2, then I multiply by the limit of x squared, which I just get by plugging in the 2. And then I add 5 times the limit of x, bring the 5 down, take the limit of x by plugging in the 2. So the limit of a constant is just our constant, just like we said here. And then we're adding those and then subtracting 1 from it. We're adding these 3 functions together, this function, and the function y equals -1, or you can think of that as subtraction, subtracting that function, y equals +1. You're going to get the value that you expect. So you do the computation. And in this case, we get 17 for our answer. So it's very, very simple. And this is very similar. And if I take the product of 2 functions, and I know the limit of this function is L and the limit of this function is K, you just multiply them together. Provided those are finite, you're good to go. And if I'm taking the limit of the quotient of these functions as x approaches c, if the limit of the numerator as x approaches c is L and the limit of the denominator as x approaches c is K, we just get L divided by K, provided that the denominator is non-zero. And then the final limit for our limit laws is this one, which is just an example of a limit of a composite function. We're taking the limit as x approaches c of f of x raised to the n. We're going to get L raised to the n, provided that L raised to the n is a real number. And if that is a square root, if n was a 1/2 power, we would need to make sure that L is non-negative in order to get a real number. If L was, or if n was 1/3, well, then we'd be fine. The L could be any real number, and we could take the 3rd root of that. So we just want to make sure that the answer actually makes sense in the real number system, because we're talking about real valued functions of a real variable, at least in calculus 1, 2, 3, and ordinary differential equations for the most part. Now this is the limit of a composite function. This is just a fact from the textbook, and I think it's proved in the appendix. And that's the appendix of the Larson calculus text, 10th edition. And it just says that if the limit as x approaches L of f of x equals f of L, and the limit as x approaches c of g of x equals L, then the limit of a composite function is just the outside function evaluated at the limit of the inside function. So you can basically pull the limit inside and compute that limit, figure out what that answer is, and then plug that value into the outside function, and that's going to give you the right answer. But here's a particular example. But again, when I'm actually evaluating this, I'm not really thinking through that limit of a composite function fact or theorem very often. I'm just thinking, if I plug in x equals 2, do I get out an answer that makes sense in the real number system? If it does, if we do get an answer that makes sense, then we're talking about a function that is made as a composite function of those known functions that we talk about. Polynomials, rational functions, root functions. All those functions that we discussed in an earlier video. Then we just plug in the 2. So we get the 3rd root of 2 times 2 squared plus 7. So I've got the 3rd root of 8 plus 7, which is the 3rd root of 15. I don't know what that number is, but it's just a real number. And it's fine to take the 3rd root of any real number. So that would be our answer. Now, if we wanted to talk about sort of an inside-outside function version of this, the outside function would be that function that we are applying to that polynomial function. So f of x is the cube root function. And the cube root function is continuous at x equals 15. So all we would do is plug in 15. The inside function is this polynomial, and it's continuous at x equals 2. So to get the answer, we just evaluate the limit of this, which gives us the 15, and then we plug that into this, which gives us the cube root. Again, I don't really think much about this when I do this. I just plug in the 2, and if it gives me a common sense answer, then we're good to go. So I think that's it for limit laws. Let me know if you have any questions. We're going to look at some other limits in the next example, or in the next video. I think we'll look at some infinite limits because that was related to the content we talked about last time.